Let's implement binary search in C#. This is Daniel and you are going to get coded. Here I have Visual Studio open and we need to create a simple console application. So I will go to File, New Project, under Visual C#, Windows Desktop, Console App. I'm going to say binary search. And then hit OK. While this is loading, I have a link open right here. You can find the link in the description down below, hopefully. Okay, so one tip before we start, you don't have to implement this yourself. You can use the built-in method showed here. So if you remember, or if you watched the video, I'll put the link right here so you can watch it. That video explains top 10 array methods that you should know in C#. One of them is binary search. So you don't have to implement this from scratch. You don't have to implement this by yourself. You can use array.binary search, and this is a more optimized, a more efficient way of searching an item in an array. Okay? But if you don't want that, and if you want to actually know the behind the scenes of a binary search, you are welcome. Let's try to start. So I'm going to go back, and then in order to binary search an array, it has to be sorted. So this is like the prerequisite of applying binary search, to have the array sorted. So it has to be sorted in ascending order. Okay? You can simply use the array.sort method, which I'm going to use in this example. So this is the same thing that I'm going to use in this video. If you are curious how to sort arrays, then check this post over here. So this is another video. This video explains quicksort. And I truly advise you, if you want to know how to implement binary search, that you should go and watch that video first. Because binary search implementation, so the implementation of binary search, is quite similar to quicksort implementation. Okay? So if you watch that video first, it will be easier for you to actually understand what binary search does. Okay? So let's scroll down and start implementing. Let's create an array with numbers and sort it. So this is just a simple array of numbers with some random numbers. And again, because I want to have the same numbers, the same values as in the post, I'm going to use these exact same numbers. So in the main method, I'm going to start by saying var numbers, and then new, square brackets, and then I have 1, 5, 0, 34, 3, and 9. And I forgot an extra space there, but if you forget, you can press Ctrl+KD. The file gets formatted. Okay, we also want to sort. So again, a prerequisite for binary search is to have the array sorted. So you need to sort the array. Otherwise, binary search won't work. So array.sort, and this is going to be our numbers array. And also later on, I'm going to print to the console some things, so it makes sense to actually say console.readKey to see what values I want to print to the console. Okay, before we actually implement binary search, I want to have a look at linear search. So if you are not familiar with these searching algorithms, linear search is the most common, the easiest search algorithm in programming. So what it implies is to go one by one and check if that item is what we are looking for. So if we have an eye on the linear search method, we see that we pass an array and an item. That item we want to search and we want to get its position, so its index in the array. And we just have a for loop, so we go from array index 0 until array.length, so until the last element in our array, and then we check to see if that specific item over here is the one that we are looking for, so if these two are equal. In that case, we are returning I, we terminate the for loop and the method, and we get the result. So imagine this. You have an array of numbers, 2 million numbers, index 0 and the last index. Okay, this is going to be 2 million minus 1, okay, the last index. And maybe the item that we want is at the last position in our array. We need to go one by one, one by one, one by one, each item to actually find that specific item, that specific index of that item in the entire array. That is going to be just so long. It's going to take so much time. It's going to be inefficient. It's not performant. It's not any of that. But again, this is the easiest way. So I'm going to implement this very way right now. And then I'm going to transform it into binary search. So private static int linear search. And then I'm going to pass the array as a parameter. And then I'm going to pass an int item, which represents the item that we want from the array. And then we need a for loop. So for tab tab, we need the I indeed, and then we need array.length, okay, and enter. Inside the for loop, we have a simple if condition, which checks to see if the actual item that we have come across is the item that we are actually looking for. So array I, array index I equals item. So if array index I is equal to item, enter, then we are going to return the I. Otherwise, if that item is not in the array, if no item is actually equal to that one, we are going to return -1. Why am I returning -1? You know that arrays start from 0, so computers start counting from 0. If you don't know that, please check this video over here. Because of that, because arrays start from 0, we can have an item at the first position, so index 0. So if we return 0, it means the item is the first one. So we don't want that. We want something outside. And the first value, which is outside, is -1. So whenever we call linear search, the linear search method, and we get -1, we know what happened. Because we know how the linear search behaves, it returns -1 if the item is not present in the array. And we can have some if statements or some try and catch statements based on this value, if this is what we want to implement. So this is why I chose to have -1. Okay, and let's call it to find the position or the index of value 3 inside our array. So I'm going, after I sort the array, so again, it has to be sorted, I'm going to say var index linear search numbers and 3. Okay, one small correction. I said something a little bit wrong, so I said it has to be sorted. Well, it has to be sorted for binary search. For linear search, it doesn't have to be sorted, because with linear search you can find the item because you go one by one, one by one. The actual sorting is required whenever you want to apply binary search. So a small correction of what I said previously. So let's try to press F5 or start by clicking the start button, and we get index 2. So I hope you see index 2 over here. If not, I will try to actually zoom in a little bit by changing the font size. So you see index 2. Why is index 2? Because it's sorted. So the first item is 0, the second item is 1, the third item is 3. The third item is found at index number 2. So 0, 1, and 2. This is why we got 2. But I have a warning over here. The reason we want to implement binary search is because it's much, much faster than a simple linear search, as I said previously. So let's have a look at binary search. This is the algorithm for binary search. It's not that much. It's definitely more than linear search, but it's not that much either. It's less than quicksort. So I'll try to go one by one each line to explain what it does. But before that, I want to give you like a brief explanation of how binary search works. So similar to quicksort, in binary search, you have two indices, 0 and the end of the array. And then you want to go into the middle, to the center of the array. And you check, is this middle item the one that I'm looking for? If it is, then I will just return the index. If it's not, I'm going to compare it. Is the item that I'm looking for less than the middle? If it's less than the middle, we are going to look only at this array. If it's greater, if it's bigger than the middle, we are going to look at this array over here. So we are actually, on each step, on each condition, on each time we actually try to see the middle and the item, we are splitting the array in half. So this is the full array, and then half, and then half, and half, and half, and half. And this is way quicker because we don't have to check every item from the beginning till the end. We can check only the middle ones, and we can assert based on that, meaning we can say if it's less, it's obvious in the left side. If it's greater than that, it's obviously in the right side. I don't need to check in the left because it's not there. The array is sorted ascendingly. It doesn't make sense to go to the left. Okay, so I don't know the exact number. If you have like 2 million numbers, I think you are able to apply this algorithm, I think 10 times. For sure I'm wrong, but like instead of 2 million times, like something crazy, 10 times, 15 times, 20 times, I don't know. It's going to narrow it down. So you have to divide it by 2 many times. And also it depends the probability to actually find that middle one. So yeah, this is the actual idea of binary search. So let's see it how it is implemented in C#. And I'm trying to go line by line, and to actually explain what they do. So the two lines at the beginning are for left and right variables. So we assign a left and we assign a right, the first index and the last index. So 0 and array.length -1. So we get the full array. And then while left is less or equal than right, it doesn't make sense that the left will go beyond right. It has gone way too far. So the left has to be always smaller than the right. So even though they actually, one of them increases, so even though the left index increases as we are searching, still if it goes beyond the right, we have gone way too far. So inside the while loop, I have a middle. So I go right to the middle. And I say left plus right divided by 2. This is the average. So a simple average from math. We get the average by summing them up and then dividing them by 2. Then we have our first if condition. If this item at the middle is the one I'm looking for, give me the index. And we are done. Otherwise, we still have to check other parts of the array. And we have this condition. If the item is less, go to the right. If the item is greater, so else, go to the left. So the right is going to get middle -1. Y is going to go to get that. So 0, array.length -1. We go to the middle. The middle item is not what we are looking for, and the item is less. So it makes sense to go to the left side. Okay, so the right is going to decrease from array.length -1 until middle -1. At the middle, we don't have the item that we are looking for, -1. So we don't care about the whole part over here, the whole right part. We can decrease the right index until middle -1, and we can check only on this array. And again, the same goes for this part. We can check the middle, so we are going to check the middle. If this is greater, so the item is greater than the middle, we are going to move the left to the middle +1. And then again, and we narrow it down until we actually find the item. So again, binary search, you have the whole array, and then you split it into half. And then again, half, and you got the array. You got the item from the array. So this is how it works. Okay. So I will still try to keep this implementation, and I'm going to implement it underneath. So beneath the linear search. So I'm going to say private static int, not indexer, but int, and binary search. And I'm going to have int square brackets array, so the same parameters as before, int item, and I'm going to say int left equals 0, int right equals array dot length -1, and while left is less or equal than right, so as I said, you don't want to go beyond with the left index beyond the right index. If that's the case, we have reached the end, the item is not in the array, and we return -1. If that's not the case, we are going to try to see if it's in the middle, and I forgot to actually create a middle. So before the if, I'm going to press escape. Here I need to define the middle, so middle is going to be left plus right divided by 2, so a simple average from math, and then I can say middle equals item, and I kind of not need the curly braces over here because I'm not going to add any other. I'm going to say middle, and let's do the same. So if the item is less than the one from the middle, it makes sense to go to the left side, so the right index goes middle -1. So item is less than array middle. We are going to say right is going to be equal to middle -1. Otherwise, left is going to be middle +1. Okay. If we have not found it, return -1 is not in the array. So let's try to continue. We can call to search the same value. So instead of linear search, I'm going to say binary search. And let's press F5 and see the actual result. And you can see index 2, the same as before. The array is sorted. We got the index 2 because the number 3 is at index 2. So it's the third item in our array. But I want something more from you. Recursion. There is a quote. To iterate is human, to recurse is divine. We need to be smarter then. So we are trying to iterate, but we want to have recursion. How can we implement recursion for binary search? We are going to see this right now. So let's implement the binary search as a recursive function, a function that calls itself, and we can remove our while loop. And this is the actual idea of having a recursive function. Whenever you implement recursion, you're actually replacing a for loop or a while loop or something that loops, that continues, that repeats a couple of times. This is the actual recursion. So I'm going to actually rename this to binary search recursive, to be more specific. And then you can see that I pass something. I have two more arguments, two more parameters in the method, int left and int right. So before the item, I want to pass int left and int right. And let's try to see inside what I have. So right now, because we passed them, we don't want to define them anymore. Makes perfect sense. And as I said, we are building recursion. We are implementing recursion. We don't need a while loop. We need an if statement. And right now, you can see that I have a slightly different thing. Here, right is greater or equal than left. Here, left is less or equal than right. The same thing, right? So if you know math, is the same thing. This is how I wrote the post. So I could have written based on the first one, but I don't know what happened. But the same is the same idea. If you know math, you have no problem understanding this. Is the other way around, okay? So I will try to keep this the same, and I will make sure that I apply the same things. Or let's try to make sure that this is going to work. We can just apply this thing over here. But I assure you, they are the same. So if right is greater or equal than left, var middle is going to be left plus right minus left. So you are able to do this. You are able to actually not go to the middle. You are able to like reach out and say left plus the average. This is not what I want right now. So if you know why this is the case and why this works, you can comment down below. But I want to make this simpler. So I know some implementations offer you this idea of having this extra number value there, but I prefer having this one. So left plus right divided by 2. If array, the middle one is equal to item, return the middle. Otherwise, we are going to do this. And so you can see we have, again, the different things. So this is like the mirror thing. It will work otherwise, but let's try to write it as it is in the post. Greater than the item. And then this is the actual recursion thing. So I will not just try to remove it. I'll try to actually explain what I mean here. So by a recursive function, you call itself. You call the function from itself. So we are going to say return binary search recursive. Sorry about that. Let me try again. Binary search recursive. I'm going to pass the array. And now I'm going to pass left. And the new value for right is this one, right? Middle minus 1. I'm going to cut and paste here. It's the same over here. Okay? So nothing changed that much, just the calling of the method. And we are going to do the same. Return binary search recursive array. Right now left is middle plus 1. We want to sectionate. We want to partition our array. We want to split the array, okay? And then the right remains the same. And then we pass the item. We are trying to find the same item. We don't temper, we don't change the item. Okay, so as far as I see, these look the same, hopefully, beside this left over here. So if you know why this can help our algorithm, please comment down below and you can help us all, right? So let's try to see. Then, because I want to call it simply as before, I will create an overloaded version of binary search recursive. Okay, so this is an important idea. Let's try to talk about it. Right now you can see that I call binary search recursive, I pass the numbers and I pass the item that I'm looking for. This is what I want. But this is not going to work because I have to pass left and right. So I can do that. I can pass 0 and numbers dot length minus 1. And this works. And if I run it, it will work. But imagine doing this a couple of times. And you have to pass the same logic. 0 numbers dot length minus 1. 0 cards or cats or reports dot length minus 1. It's redundant. And you should keep your code dry, meaning to not repeat yourself. So we don't do this. So we kind of need to actually get that away. This happens for every array that has to be searched. So why not creating a method before binary search recursive and calling it the same, and in that method we have 0 and array.length minus 1. This is what I mean by having this method on the left side. So it's the same method, and I'm going to implement this method, and then I'm going to explain what is an overloaded version of binary search recursive. So let's try to write it first, and I'm going to say int binary search recursive, and I think I want to copy this one because we have too many things to write. Int array, and then int item. And inside, I'm going to call the other one. So I pass this one, I call this one first, and then I'm going to pass to the other one. And I'm going to get this one from here. So cut this one, paste this one here. And instead of 3, we don't just check 3, we check the item. So this has to be generic. And instead of numbers, we are passing array, so we can search on an array in general. And this one has to be returned, so we have to return that value. So you can see we have no errors beside this one. So we want to call the first one, so binary search, recursive. And once I write the parentheses, you can see that I have here one of two. If I press on down arrow, on the down arrow, you can see the two different versions. Binary search with these 4 parameters, binary search with these 2. Depending on the number of arguments that I'm passing to these functions, to this method calls, that specific method is going to be called. So if I pass only numbers and then 3 because I want to search for 3, C# knows that I'm talking about not that one but the first one, the binary search recursive, which has only 2 parameters. It knows that. This is the actual overloading of a method in C#. You need to have the same name but different parameters, different types of parameters, different numbers. So either different numbers or different types. This is the actual difference between 2 versions. Okay, so I think it's clear enough what I've done here. Let's try to press F5 and see the actual result. Hopefully we get 2 again, so we do. So this is right now recursive. We are not using a while loop, we are smarter, we are trying to actually call itself a couple of times and return that result back. The actual result is the index or the position of the item. Okay, so we've done that. Let's summarize. This is the binary search. You can find the source code on GitHub, so I'm going to provide in this post over here. So if you click the link in the description down below, you are going to go to this post, and here you can find a link to GitHub. So you can find the whole code on GitHub. You can work with it, you can try it out. If you have problems right now implementing it, you can find the code right there and you can use it. So I hope you understood the code from today. If you did, please click thumbs up. Don't forget to comment down below your questions, other improvements that you might have in regards to my code over here. Until next time, bye guys.